Hello and welcome, class. Welcome to another lovely day of lecture. Whether you are watching this in the morning time or the evening time or somewhere in between, hello and welcome. We're going to get started with a brand new chapter, chapter 15. Reaction rates now are sort of behind us, but not entirely behind us. As we will see, the conversation of reaction rates is going to perfectly transition into this concept of equilibrium. The reason why is our description of equilibrium, like as we currently understand it, is very much so dependent on reaction rates. Before getting started with this, though, I am going to acknowledge that we are starting a brand new unit, this last unit of the semester, and it will very nicely mirror the last unit that we talked about last semester, which was Chapter 9. In Chapter 9, we talked about solubility / precipitation. We talked about acids and bases, as well as neutralization. And we talked about, I'll just write it down here, redox reactions / oxidation states. So the conversation here, as we were kind of getting into the concept of solution chemistry, specifically in the concept of, or in the context of aqueous solutions, each of these discussions here talking about precipitation reactions, neutralizations, what does it mean to be an acid and a base, etc., were all sort of incomplete discussions. For instance, with solubility, we had talked about things, compounds in solution being either soluble or not soluble. It was either one or the other, yes or no. We didn't really get into the detail of the in-between when things are sort of soluble. What we're going to be doing now in this last chunk of this semester is opening up each of those cans of worms, talking about what it means to be partially soluble, what does it mean to be a partial acid or base, what does the complexity of a redox reaction actually look like and why? So we're going to be talking about each of these, but in order to have those more detailed conversations, we need to first get into what it means to be in equilibrium in a chemical sense. And so the concept, or the conversation all around equilibrium, is going to also circle around what it means to be a reversible reaction. These two concepts are kind of inherently linked together at the general chemistry level. So we're going to be talking about what is a reversible reaction and how can we talk about it in the term or in the sense of a dynamic equilibrium, and what does that mean? Okay, so reversible reactions. Everything that we had been talking about in the context of complete reactions, reactants going from reactant to product 100% of the time, throw it out the window. We're not going to be having those conversations anymore. They were very nice, very convenient, but sadly most of the reactions that we're going to be talking about for the rest of the semester, and in fact most of the reactions that occur in the world period, fall under the umbrella of reversible reactions. These are reactions that go from reactant to product simultaneously. Product is going to be turned back into reactant. So as I have written here, reactants are simultaneously converted into products, which are converted back into reactants, which are ... This process, this cycle of reactant turning into product and product turning back into reactant is constantly happening. So reversible reactions, for that reason, are not complete. There is no limiting reactant, there is no excess reactant, there is no theoretical yield, no percent yield that we can meaningfully measure based on stoichiometry. Stoic is still going to be useful to us, but not in the complete sense that we have been talking about it thus far. We're going to have to be almost framing the conversation of stoichiometry in this whole new light of reversible reactions. So this generic reaction, as it is listed here, A plus B, is going to be reacting reversibly, hence this back and forth arrow, with C and D. This is going to be one of our new best friends. So we're going to be seeing this generic reaction a lot as a means to describe equilibrium in a more general sense. But before getting into too generic or too general of a conversation, let's lay out an example of a reversible reaction so we can kind of sink our teeth into exactly what it is that we're talking about. And we're going to frame that conversation in terms of reaction rates. So reaction rates we've just finished talking about, Chapter 19 was all about reaction rates, the mechanisms, the rate law expressions, integration, time, all of that is still going to be in the back of our heads as we're having this conversation about equilibrium in a chemical sense. So as it is written here, a reversible reaction is at equilibrium, and when we say at equilibrium, what we mean is that the reaction is quote unquote finished. It's not to say that a reaction is finished when, or at least a reversible reaction is finished when all reactant has turned into product. That is not the case. A reversible reaction is going to be finished when the forward rate is going to equal the reverse rate. And there's one big clue as to when this happens and what it looks like in terms of concentration versus, on this x-axis here, we're going to have time. So when these two rates are equal, when forward rate is equal to reverse rate, the concentration of the reactants in products are going to be constant. We will see no more change in the concentration of reactant and product. So let's look at this concentration versus time plot here, corresponding to the reaction of dinitrogen tetroxide decomposing into 2-nitrogen dioxide. So in this reaction, our quote-unquote reactant, our N2O4, we're starting with some certain concentration. It doesn't really matter what it is. We'll just say X molar. And as the reaction progresses, as this N2O4 decomposes, we can see that the concentration of it is going down at a certain steady rate. We can also see that the concentration of the product as the reaction is getting started is increasing, right? We are forming that product. But eventually, what we're going to see as the product is being produced, the reactant is being totally used up, it's being consumed. There's a point, and on this graph it appears to be approximately right here, where the concentration of our NO2 and N2O4 are now constant. Right, we have this steady line horizontally, meaning that concentration now, as a function of time, is no longer changing. This is not to say that our N2O4 is not turning into N2O2, it's just that the rate that this is happening as the reactant is turning into product is the exact same rate with which the product is turning back into reactant. And as a result, we see no meaningful change in the concentration now of the N2O4 or the NO2. We are now looking at a constant, steady state. So even though this reaction is still constantly happening, there is a dynamic, meaning that there is change occurring, right? There is movement, there is change. There is a dynamic equilibrium. It's not like the reaction is just totally stopped. It's still ongoing. It is dynamically occurring, but we're going to say that the reaction itself is finished because now there's no change occurring that we can see, no meaningful change. The concentrations now are the same, and they will remain the same forever unless there is some type of disturbance in the system. Okay, so how can we then quantifiably connect concentrations to this new concept of a reversible reaction or a dynamic equilibrium? Well, we're going to use the reaction rates idea again to kind of help us out here, since what we had just defined is that the reaction rate in the forward direction, where here the F stands for forward, of the reaction that we just talked about. This is the same reaction, the N2O4 decomposing into 2NO2 in a reversible manner, hence this double arrow, this back and forth arrow is going to, from now on, signal to us that this reaction is reversible. So as the N2O4 decomposes into the NO2, there's going to be some forward reaction rate, and that rate's going to be equal to the rate constant times the concentration of N2O4. This has been found to be a first-order reaction, so there's a little exponent of 1 up here. The rate of the reverse, though, is also going to matter, where this little r is going to stand for reverse. Since this reaction is going forward from reactant to product, but is also going in reverse from product to reactant, there's also going to be some type of reverse rate. And so that reverse rate is going to be equal to the rate constant Kr times the concentration of NO2 squared. And so this reaction rate has been found to be a second-order reaction rate, and in this case, there is no coincidence to the fact that there is a stoichiometric coefficient of a 2 here, but we'll be talking more about that in a brief second. For now, let's tie together this last loose end of if your forward reaction rate is equal to your reverse reaction rate at equilibrium, we can also say that our Kf times the concentration of N2O4 is equal to your rate constant Kr times the concentration of NO2 squared. All right, so we're going to set that then up, our Kf is equal to the N2O4 concentration, or Kf times the N2O4 concentration is equal to our Kr times the NO2 squared concentration. And so what's pretty neat about this, again, the math we're about to do is all at equilibrium here, is that we can see that we have two constants, right? Two numbers that don't change. They are a function of temperature, activation energy, collision factor. They're all kind of the background environmental terms. So let's say we want to pull all of the constants to one side. Our Kf divided by Kr is going to be also equal to the concentration of NO2 squared, all divided by N2O4 concentration. And so if we are at equilibrium, the ratio of the concentration of our products, which again we can see up on top, divided by the concentration of our reactants is going to be constant. And this we represent this type of equilibrium constant with a big capital K. This is going to be an equilibrium constant. And this constant, since if we look over here on the left, is equal to a ratio of these two other constants, which are dependent on things like, again, temperature, activation energy, collision factor A. This is an EA. The equilibrium constant will always be the same constant so long as we are at the same temperature and we are looking at the same reactant. Like if we're not adding any type of catalyst to it, this equilibrium constant will be true for this reaction always. At least always, so long as these variables are not changing. So if we're at the same temperature, if we're looking at the same reaction, again, we're not adding any type of catalyst, this equilibrium constant will always be true. This will always represent the ratio of products to reactants for this given reaction, no matter what. And so from this example, we can draw a couple of conclusions corresponding to our generic reversible reaction. So here we have, again, our A plus B is reacting reversibly to create C and D, and this reaction, again, is running in reverse. The ratio of the product to the reactant, as we had just, rearranged our previous example to be a ratio of product concentration divided by reactant concentration, here we can do the same thing for the generic reaction. The ratio of the product and reactant concentrations is constant at equilibrium. For the exact reasons that we just stated, this ratio of concentration of product divided by concentration of reactant will be equal to the Kf divided by Kr, meaning again that if we're looking at the same temperature, haven't changed the activation energy at all, this ratio will be constant and can be represented by this capital Kc for this reaction always. Okay, so now that we have talked about what an equilibrium expression is, how it is a ratio of products to reactants, here are the rest of the topics that we're going to be introducing throughout the rest of this lecture for the generic concept of equilibrium and the all-encompassing umbrella idea of a reversible reaction. Namely, we're going to figure out how do you write equilibrium expressions for given chemical equations, like how we're going to see some more examples of tying the equation and the Kc, its equilibrium expression, together more tightly. We're going to talk about what the magnitude of Kc means. The ratio of your product to your reactant is going to tell you something about the overall chemical equation and how the products versus reactants are more stable, or how you're going to have more than one possibly than the other, because equilibrium does not mean that you have equal numbers of product to reactant. Equilibrium means that the rates of your forward is equal to the rates of your reverse, and this is going to be constant throughout the rest of the semester. We're going to talk about how if you manipulate a chemical equation, that's going to change your value of your equilibrium constant. For instance, if you add two reactions together, or if you swap it, like reactants become products, products become reactants, how does its Kc change? And also, what other forms of equilibrium are there? Because we have the equilibrium constant as is dependent on our variable right now, C, being concentration. But as we will be discussing today, as well as in the rest of the chapters to come, there are many forms of equilibrium. But regardless as to what type of equilibrium we are working with, this constant, this idea that the rate of the forward reaction is going to be equal to the rate of the reverse reaction will always, again, remain true, meaning that your concentration of products to reactants, or let's say pressures, or etc., like whatever type of equilibrium we're working with, products to reactants will also always remain true. Okay, so let's get some more practice writing out some equilibrium expressions for some given reactions. Since this process is going to be the same process that we're using to write out equilibrium expressions, no matter what the reaction is, let's get some practice. So there are two different types of equilibria being the plural of equilibrium that we can talk about. The first is a homogeneous type of equilibria. This occurs when all of your reactants and your products are in the same phase. So much like a homogeneous catalyst, where the catalyst was in the same phase as the reactants, here a homogeneous equilibria is going to be represented when your reactants and products are all in the same phase. So here's a good example of that. We have H2 and Br2 both in aqueous phase, reacting reversibly to create some hydrobromic acid, also aqueous phase. And so the Kc expression for this, I'm definitely going to invite you to pause the video, see if you can't write out the equilibrium expression yourself. First, double check your answer to mine. And my answer is going to then be a Kc. And we're always, again, going to be doing products over reactants, corresponding to how the reaction is written above. Because yes, this reaction is reversible, meaning that your products could have been written as reactants and reactants could have been written as products, but your Kc, your equilibrium constant expression, is always going to correspond to the reaction as it is written. So your reactants, for convention's sake, will still be on the left, and your products, for convention's sake, will still be on the right. And so from this, we can say that our Kc, or equilibrium constant, as is dependent on concentrations. And yes, there is a subscript of a C because there will be other forms of an equilibrium expression that we'll talk about, but we're going to be focusing on concentration first. So this is going to be equal to concentration of products divided by concentration of reactants ratio. So here we have a concentration of our one product being an HBr, and we're going to raise this concentration to the 2, since there is a 2 in front of the HBr. The reactant concentrations are going to be an H2 times a Br2. And since there are only stoichiometric coefficients of 1 in front of the H2 and the Br2, there's going to be a 1 in front of the H2, a 1 in the exponent of the H2, and a 1 in the exponent of the Br2. And so this is going to be our equilibrium expression as dependent on concentration for, or corresponding to, this reaction above. So once this reaction reaches equilibrium, this ratio of products to reactants then will be true. Heterogeneous equilibria are sort of, the hand-holding partner of the homogeneous. The difference then, again, similar to the catalyst example where the heterogeneous catalyst was in a different phase of the reactants. Here, not all of the reactants and products are going to be in the same phase. Not all of them. So most reactions that we can see and work with in aqueous solution are going to be some type of heterogeneous equilibria. And the key difference here when it comes to writing an equilibrium expression for this type of equation or this type of chemical reaction is that only variable concentrations are going to be included in your equilibrium constant expression. This is not to say that the concentration of anything that is not variable doesn't matter to the reaction rate, but when it comes to looking at ratios of products to reactants, ratios, so the combination of the ratio of these rates, any variable that doesn't change concentration ends up not mattering to the equilibrium constant since it gets canceled out, right? A constant number divided by a constant number becomes 1. And so to make our lives easier, we are not going to include any species that doesn't have a variable concentration. Okay, so what does that mean? A variable concentration means that your phase is going to be aqueous or gaseous. Since in an aqueous solution, we can have varying numbers of moles to volume, right? We can change the concentration here. Or similarly with a gas, according to PV equals nRT, pressure is variable with numbers of moles, right? That was like Avogadro's whole shtick, was that you can change the number of moles of a gas that you have and change the pressure, change the volume, change the temperature, etc. as a result. So these two phases are always going to be phases that are going to be included in your equilibrium constant. Phases that are not going to be included, phases that are not variable, are going to be things like liquids and solids. Since liquids and solids have constant densities, right, when we were talking about condensed phases getting into chapter 12, this was one of the things, this factors was what set a liquid and a solid apart from a gas. These things have constant densities, whereas gases have variable densities. So since your liquids and your solids have constant densities, they also have constant concentrations. You can't change them. And so for that reason, even though in this given reaction below, where we have acetic acid interacting in water to create some acetate ion and some hydronium ion, H3O+, the water concentration over the course of the reaction does not change because it is in liquid form. It has a constant density, therefore it has a constant concentration. And so your Kc, your equilibrium expression, is only going to include the products that are in aqueous phase and the reactants that are in aqueous phase. So the products that we are going to include are going to be both of them. We can see both the acetate ion and the hydronium ion are in aqueous phase. Since they're in aqueous phase, they can have varying concentrations. The CH3COO minus concentration will be multiplied by your H3O plus concentration, and all of this will be divided by the acetic acid CH3COOH concentration. It should be 1C. Okay, so thus far we have two big rules when it comes to writing our equilibrium expressions. The first rule is that we're always going to be looking at products over reactants. Always. Every time. Our second rule is that if a species apostrophe, if that species is not in some type of variable concentration form, in other words, liquids or solids, we are not going to include them in our equilibrium constant expression. Because the concentrations don't change, there's no reason to include this in a ratio of concentrations because it's always going to be constant. It will always cancel out when we are comparing equilibrium constants. Okay, so let's talk about the magnitude of your equilibrium constant. What does it signify? What does the number mean? Now, we are going to be looking at some specific examples to see what these types of numbers look like, but before laying out any specific example, let's look at what the numbers could qualifiably mean, and then we'll put them in a context. So the magnitude of your equilibrium constant is going to signify how complete versus how reversible a reaction is. So in the case where your equilibrium constant, or the ratio of product to reactant, is going to be huge, significantly greater than 1,000. That's what this means. If your equilibrium constant is super, super big, like bigger than a ratio of 1,000, what that means is if we look at our equilibrium constant expression, like the most generic form of it, where we have products being multiplied in the numerator, we have, numerically speaking, a ton of product. A ton of product to make this first situation true, right? If our equilibrium constant numerically is a very big number, that must mean that we have a very big numerator. So this first scenario, this first situation, is going to represent a complete reaction in the forward direction. In other words, all of the reactions that we have been talking about up until this point, all of our complete reactions, if we were to work out the math, would have equilibrium constants that are significantly larger than 1,000. These are going to be reactions that are very, very complete, that have very, very little reactant and a ton of product. The other situation that we have talked about, like in a non-spontaneous reaction or a reaction that just doesn't move forward on its own, is going to be laid out in this second situation here. So if your equilibrium constant is much, much smaller than 1,000th, right, this 10 to the negative 3 means that your Kc is going to be very small. And if it's very small, algebraically speaking, if we come back over to our generic expression, that must mean that our denominator in this case is going to be very big. So in other words, if we're working in the situation where we mix two species together and we have a ton of reactant still sitting in the beaker, what this tells us is that there was no reaction. Nothing happened. However, what this also signals is that if we were to have mixed the products together, more than likely we would have ended up with a forward reaction. In other words, if our Kc is very, very small, meaning that at equilibrium we have a ton of reactants, the reverse reaction will be complete. Okay, so far we've kind of linked the equilibrium expression, this idea of the ratio of products to reactants, to the previous situations that we have talked about, either a reaction being complete in the forward direction, or in the instances that we have witnessed no reaction in the forward direction, what this really means is that the reverse reaction will be complete. And this is signaled by a very, very small equilibrium constant. So the situations that we are going to be getting ourselves into now, the most commonly, are going to be those where our equilibrium constant is going to be somewhere in between these two extremes. So our equilibrium constant is not going to be incredibly tiny, it's not going to be incredibly big. It's kind of like a Goldilocks situation where in between we are working with true dynamic equilibria. We are working with true reversible reactions. Reactions where it's going to matter whatever this equilibrium constant is. And this equilibrium constant will tell us a little bit about the nature of the reaction, since we are going to have a meaningful concentration of both reactants and products. Okay, so let's look at this equilibrium expression example. So we have a given reaction here. Again, we're going back to our N2O4 reaction. And it's going to be decomposing into the 2N2 or NO2s. So this reaction is going to be moving back and forth. So we can use the concept of our equilibrium expression, which we've already written for this reaction, right? The concentration of our product, NO2, up into the, is squared, this stoichiometric coefficient being raised into the exponent, and the other concentration of our reactant, the N2O4, is going to be in the denominator here, right? Ratio of products to reactants at equilibrium will be constant for this reaction, following the graph that we had already witnessed where the concentration sort of leveled out. So let's say we're looking at a trial 1 versus trial 2 situation. What we want to do is use trial 1 to calculate numerically what Kc is going to be equal to. Then in trial 2, where we have the Kc, we can use it to find a missing concentration when the reaction is at equilibrium. And that is going to be the crux of this type of problem that we are introducing here. We need to be at equilibrium in order to just straight up use this equation as we are going to be using it. So that's the big assumption. We are assuming, as is labeled with these concentrations here, that we are at equilibrium, that the reaction now has reached a steady state where reactants and products are moving backwards and forwards at the same rate. Okay, so the way that we can use this equation is we can take the concentrations numerically that we have recorded here at equilibrium and insert them into our equilibrium expression here. So the concentration of our NO2 we can see here is a 0.0547 molarity squared coming from this square up here. Going to make sure that we don't lose that squared because it will definitely affect our math in some way. The concentration of our N2O4 at equilibrium, we can see here, is a 0.643 molar. Okay, so here I'm going to bite my tongue a little bit because I harp on units a lot. Units tell us a lot about a chemical equation, about a mathematic equation, how everything kind of links together. We've been following the units, quote unquote, this entire semester. Now I'm here to tell you that in any conversation we have about equilibrium, setting up an equilibrium constant like so, the units don't matter. In other words, there is no one big unit for the equilibrium constant. It's going to depend completely on the reaction that you're working with. And so for that reason, since it's so tied directly to the reaction that you're working with, and it doesn't really give you a lot of useful information, we are no longer going to be including units in this type of problem. So in other words, we're going to be taking 0.0547 squared, dividing it by this 0.643, and this is going to give us a value that is equal to 4.65 times 10 to the negative 3. And there is no unit here. This is going to be a unitless ratio. And that's the biggest reason as to why we are going to be dropping these units, is because it's all about ratios. We're all working in the same unit here, the same units in the numerator as the denominator. The specific number of the units that we have doesn't matter. It's all a ratio of concentration. And so this value is going to be unitless. I only ask that you do not forget that this is a unitless value because we're looking at ratios of concentration units here. And so we're going to say that they, quote unquote, cancel out. Even if they don't quite cancel out, for informational sake, they cancel out. This could be a little bit of a problem for anyone who has been following the units, who's gotten into that habit, and now you're suddenly unitless when it comes to this type of problem. Just don't forget the context of what you're working with. It's all about the ratios of concentrations. If you remember that, you will still be fine. Okay, so we've just found that the Kc for this given reaction at a constant temperature is going to be 4.65 times 10 to the negative 3. This is going to be true no matter what trial we are working with. So long as the temperature is the same, this Kc is going to be the same. Meaning that the ratio here of products to reactants, again, so long as we are at equilibrium, will be true no matter what the concentration of our product to reactant is going to be. 0.378 is now this new concentration in trial 2. We don't know what the concentration is of the product, but given that this reaction has reached equilibrium, as we are being told by these little subscripts of an EQ here, we can use our equilibrium constant to rearrange and solve for the concentration of NO2. So the way that we can mathematically do this, let's get rid of this, because we are going to be working with square roots, cubed roots, all types of roots. The way to rearrange and solve for this Kc then is going to be concentration of NO2 is going to be equal to the square root of the concentration of the N2O4, that's 0.378, times the value of our Kc. For the sake of space, I'm just going to write Kc, but this whole value, the 4.65 times 10 to the negative 3, is going to be right here. We're going to square root all of that. This is going to give us a concentration for the NO2 that is equal to 0.0419. And this will have a molar now return back, since it is a concentration in the units of molar. Okay, so let's take a quick beat before moving forward to make sure that this value actually makes sense. So in trial 1, the ratio of product to reactant, we can see that the product concentration was a 0.0547, and the reactant concentration was a 0.643. Well, between trials 1 and 2, we can see that the concentration of the reactant decreased. What this means is that the concentration of our product must also, let's see if I can write this sideways, decrease between trials 1 and 2. This is because we still want that ratio of product to reactant to be the same. Well, if your reactant decreases, then your product must also decrease to keep this ratio mathematically equivalent. So that's going to be a double check for us. We're always going to be looking at what is the ratio of products to reactants here. And does the answer that we're calculating line up with that consistent ratio of products to reactants. Okay, so equilibrium constants, now that we've kind of started tying them to numbers, quantitatively speaking, can also be manipulated. So reversible reactions, much like complete reactions, can be added together, they can be written in reverse, they can be scaled up, they can be scaled down. And so what we're going to be doing now is looking at how does the equilibrium constant, which gives us information about that reversible reaction, how is it affected by these types of manipulations that we can make. So the first example we're going to look at is what happens when you write a reversible reaction in reverse. Since a reversible reaction can meaningfully be written in reverse, right, this is telling us, this first situation is telling us the exact same thing as this second situation, that we're working with a reversible reaction, and that N2O4 is turning into NO2. Only in the second case now we're saying, oh, well, two NO2s can be synthesized to make N2O4, but that's the exact same thing as when our first reaction goes in reverse. However, for, again, consistency's sake, we're always going to be looking at whatever is on the left is the reactant, and whatever is on the right is going to be the product. And since your equilibrium constant is always going to be a ratio of product to reactant, in reversing our chemical equation, this is also going to change how we see our equilibrium constant. So the equilibrium constant for the first situation, our K sub capital C, is we found was equal to 4.65 times 10 to the negative 3. Well, if we reverse the reaction, our new Kc, which is going to be equal to the concentration of our product, which is the N2O4, divided by the concentration of our NO2 squared, we can see here that this expression is the exact inverse from what the first reaction was, right? We calculated our first Kc because our concentration of NO2 squared was divided by the concentration of N2O4. These two things, these two expressions, are the exact inverse of one another. So in other words, if you have a reaction that is written in one given direction, like our N2O4 decomposing into two NO2s, if you reverse this reaction, what's going to happen to its equilibrium constant is that your new equilibrium constant will be equal to 1 over your old equilibrium constant. So our new equilibrium constant is going to be equal to 1 divided by 4.65 times 10 to the negative third, and this is going to give us a value that is equal to 215. Now, regardless as to whether or not this reaction is written in the forwards direction or is written in the reverse direction, this is gonna, like the two values that we have here are gonna tell us a little bit of something about or a little bit of information about the reaction. The first situation, the first reaction as it's written, we see that we have a smaller equilibrium constant than if it's written in the other direction. What this is telling us is that the ratio of, in the second situation, our product, is greater than the concentration of our reactant. The reason why we can draw that conclusion is that our value here, 215, is definitely larger than 4.65 times 10 to the negative 3. This is a value that is greater than the ratio of 1, meaning that you're going to, numerically speaking, have more product as your reaction is written than reactant. In other words, you're going to have more N2O4 than what you have NO2, regardless as to how you write this reaction. Or another way that we can manipulate these chemical equations is if we write a reaction that is the sum of like two types of constituent reactions. So if we take our first reaction here, which is the, again, same reaction that we've been working with, our N2O4 is decomposing into two NO2s. Its equilibrium constant, as we have seen, was 4.65 times 10 to the negative third. The second type of reaction is another reaction that's been demonstrated to be in some type of dynamic equilibrium, reactants and products, kind of all existing in one beaker, one pot. The two NO2s are going to be, in this case, decomposing and reacting to create two nitrogen monoxides as well as an oxygen gas. This is actually a reaction that we looked at when discussing the reaction mechanisms in Chapter 19, so now we are kind of divulging that this reaction can be considered meaningfully to be a reversible sort of reaction. The exponent on its equilibrium constant is very small, meaning that this reaction definitely favors reactants. Again, because in the way that we write products divided by reactants, this very small number means that we have a very large denominator, meaning that we have a very large number of reactants. Needless to say, though, or regardless of that point, this is still a reaction that exists in equilibrium. If we want to figure out what the equilibrium constant would be for this third given reaction, well, all we have to do is look at what the two previous equilibrium reactions were telling us, because this third reaction is actually just the sum of reactions 1 and 2. Right, so if we add reaction 1, all of its reactants together, and add all of the products together, the two NO2s end up canceling out when adding everything together, and we are only left with this N2O4 on the reactant side, our two nitrogen monoxides, and our oxygen gas. So this is another way that we can write sort of like the combination of these two previous dynamic equilibriums. Well, if we want to know then what is the equilibrium constant representing this new equation, let's figure out what we have to do, like to the two previous equilibrium constants. What do we do to Kc1? What do we do to Kc2 in order to figure out what this equilibrium constant is? In other words, what is the dynamic nature of this third reversible reaction? Okay, so how to find this? Well, let's kind of ignore this top information. Let's just write out what is our equilibrium expression going to be equal to? Well, we have a ratio of products, our first product being this nitrogen monoxide, and we're going to square the concentration of that value since there is an exponent of 2 here. We can multiply that by the concentration of O2 gas and divide it by the concentration of our other, or of our reactant, the N2O4, the other chemical species here. Well, what we can see here is this is actually a combination of the previous two equilibria. In other words, this is equal to our first equilibria, where this product here divided by the reactant, right, dividing by the reactant, which is now down below, NO2 squared divided by N2O4, multiplied by the second reaction's dynamic equilibria, right? The nitrogen monoxide is present here, nitrogen monoxide, our oxygen gas also being in the numerator, all divided by this NO2 squared. There's a squared there. If we follow the rules of algebra, then, if we take a one fraction multiplied by another fraction, what we're really doing is multiplying the numerators and multiplying the denominators, but keeping this line kind of steady in between. What this means is that our NO2 squared concentrations are going to cancel out, leaving us exactly with the equilibrium constant that we just determined when looking at the reaction that we are working with itself. In other words, the equilibrium constant, as we can write out using our concentrations, is simply equal to the multiple of the equilibrium expressions from the first two reactions. Our Kc prime is equal to Kc1 times the value of our equilibrium constant for Kc2. So if we want to find Kc prime numerically speaking, and we don't have any types of concentrations around, all we have to do is look at the equilibrium constants for these first two reactions and multiply them together to figure out what this Kc prime is going to be equal to. Now what this value ends up being equal to, if we take a 4.65 times 10 to the negative third and multiply it by 1.63 times 10 to the negative 10, what we are left with is a value that is 7.86 times 10 to the negative 13th. The combination of these two reactions then, the first reaction and our second reaction, is going to leave us in a situation where we now have this new dynamic equilibrium that is going to be, at least we can tell by the number here, our equilibrium constant, heavily favoring the existence of our reactant. This N2O4 is going to be the most stable species, since according to the ratio of its products to reactant, we're going to have a very large denominator, a very large reactant concentration. Okay, the last way that we can manipulate these equilibrium constant expressions that we are going to be introducing here is that they can be scaled up and scaled down. So again, we're going to be looking at this N2O4 expression reacting reversibly with the NO2. if we scale up this reaction, in other words, there was previously a stoichiometric coefficient of 1, now we have doubled it. Similarly, there were 2 NO2s, now we have doubled that, we have 4 NO2s. Our equilibrium expression we can write out again from the equation that we have listed here, and that's going to give us some information about how we can use the first equilibrium constant, this known, to figure out what this unknown is going to be. Because really that's what we've been doing this entire time so far. When discussing the manipulation of these equilibrium constants, we have simply been looking at, okay, you have a reaction with a known equilibrium constant. How can you use that to figure out the equilibrium constant from this manipulated version of it? Either you've been scaling it up or reversing it or adding it to something else. What does it mean in terms of the dynamic equilibrium, and what does that value tell us? So, if we scale up our reaction, our equilibrium constant we can write out again as a ratio of products to reactants. And if you're getting tired of hearing me say ratio of products to reactants, boy do I have some news for you, because we are going to be using that phrase a lot. So the equilibrium expression, our Kc prime, is going to be equal to the concentration of our NO2 to the 4th, all divided by the concentration of the NO2 or N2O4 to the 2nd. Well, this is the exact same thing as taking our first equilibrium expression, the NO2 squared, all divided by the concentration of N2O4, and squaring it. Right? We now have an exponent of 4 in the numerator and an exponent of 2 in the denominator. This is the exact same thing as if we squared the first equilibrium constant we had. In other words, we are squaring the value of Kc to find this new Kc prime. And so your Kc prime, numerically speaking, is going to be equal to 4.65 times 10 to the negative 3rd squared. So if we double a reaction, we're going to take that factor and raise it up into the exponent of our old Kc to figure out what the new Kc is equal to. This is going to give us a value that is equal to 2.16 times 10 to the negative 5th. All right, so we can see in doubling our reaction, the equilibrium value here has actually shifted a little bit more towards the reactants, that the value of the concentration of our reactant now is going to be a little bit greater since the value of our equilibrium constant has gotten smaller. And I hope that this conversation of the relative values of reactants to products so far has been somewhat meaningful. I realize that, again, there's no dynamic conversation between you and I. So if there are any questions, I mean, absolutely, I hope you are writing it down. I hope to get a number of questions as this week progresses, so that way we can clear up any misunderstandings. But before moving forward, let's kind of recap these 3 different forms of manipulation and what, I guess in one kind of sentence, how we can describe them. So if you are writing your reactions, your reversible reactions in reverse, you're going to invert Kc to find Kc prime. That's basically what we did. We wrote our reaction in reverse between steps 1 and 2, and so to find our Kc prime, all we did was take the inverse of our first Kc. And this is going to be true no matter what type of reversible reaction you are working with, because this math of taking the inverse of your concentrations of products and reactants will always be true. So this is sort of our step 1. Our second manipulation was taking a reversible reaction and adding it to another reversible reaction. If we do this, then we are going to multiply their Kc's, which is exactly what we saw here. And the reason why, again, we saw as the math worked out, as we lay out for this new Kc prime what the ratio of products to reactants is, we saw that it was exactly the multiple of the previous equilibrium constants for the previous reactions that were added together. Again, this is always going to be true no matter what type of equilibrium you are working with. If you add 2 reactions together that are reversible, you will multiply their equilibrium constants to find the new equilibrium constant for the new reaction that results from the 2 previous being added together. And 3, if your reversible reaction is being scaled up or scaled down in some way, you are going to, raise that constant multiple into the exponent of Kc, which is exactly also, again, what we saw here. We scaled up our reaction by 2, and we see that the Kc was squared. So if we, let's say, instead increase or scale up our reaction by 3, we would actually have a 3 in the exponent here. If we scale it up by 4, we would have a 4 in the exponent. If we scale it up by 1/2, let's say, we would have 1/2 in the exponent here. You see where I'm going with this? So these are this is the recap then of the 3 previous rules, kind of in like one sentence instructions. How is it if you are manipulating your equilibrium expression, you can manipulate, or if you are manipulating your reversible reaction, rather, this is how you manipulate its equilibrium expression or equilibrium constant to give you new information about your new manipulated system. Okay, so the last topic that we're going to be talking about before I let everyone go before this lecture is finished, is the equilibrium of ideal gases. So I did say previously when discussing homogeneous versus heterogeneous and how do we know which values we're going to be putting into our equilibrium expression, the idea was that we want a species that has a variable concentration. That way, as the reaction progresses and the concentration is changing, we can actually figure out when do we hit this equilibrium where the concentration is no longer changing. And the 2 species that we are going to be including are species in an aqueous form and species in a gaseous form. Well, you can record a concentration of a gas, right, moles per liter, since the value of the number of moles and liters can be different. But we also know with ideal gases, this concept of concentration is actually proportional to pressure. And so for this reason, we can figure out or record an equilibrium constant for gases using their pressures as well as their concentrations. So both gases and solutions have variable concentrations, exactly what I was explaining here. And the partial pressure of your gas is going to be directly proportional to the concentration, which is what I've outlined here. So, since the concentration is proportional to pressure, instead of inserting concentrations into your equilibrium expression, if your equilibrium expression has a base of P, in other words, if it's dependent or based on pressure, your values that you're going to be inserting, your products and your reactants, are not going to be concentrations, but they will be partial pressures. And so the exponents we can see are going to be those stoichiometric coefficients still, but instead of inserting concentrations with that bracket notation, meaning pressure or a concentration of, we now have partial pressures, which is a big P, with a sub of your species. So this would be partial pressure of A, partial pressure of B in the denominator, partial pressure of C, and partial pressure of D in the numerator. So we're still looking at products divided by reactants, it's just now we're working with partial pressures instead of concentrations. Okay, so does this mean, though, that the value of your K is going to be the same? Well, to that, I would ask you another question in response, which is your concentration numerically equal to your partial pressure? And the answer there is no. You're working with completely different units, completely different concepts, and so Kp is not going to be equal to Kc. They're actually going to be equal to 2 different values. So if you're recording partial pressures or if you're recording concentrations, you're going to have to be careful about what type of equilibrium you are working with and make sure that you're keeping your subscripts, your C's and your P's, consistent. All right, but we can relate Kp and Kc to one another using the ideal gas law. So we can convert between Kc and Kp using this equation here. So your Kp is going to be with pressures. Your Kc is going to be with concentrations. The way that we can convert between these two then is by taking into account mathematically the ideal gas constant, which is your R, your temperature, which has to be in units of Kelvin, your ideal gas constant in this form, since we are working with the ideal gas law equation, is going to be the 0.08206 liters atmospheres per mole Kelvin. And your delta N, this is a new piece. So what does your delta N equal? your delta N is going to be equal to the change in number of moles from, well, reactant to product. In other words, we're going to be taking a final minus initial, product minus reactant, molar kind of calculation. And if we aren't given explicit values of moles, we're going to be using our stoichiometric coefficients out in front of our gaseous species to figure it out. Okay, so let's see an example of this equation in action. Let's see what the Kp of the equation that we have been working with is equal to just at room temperature, so 298 Kelvin. All right, so definitely take a break from the video, try this math for yourself. We have the Kc, it's the same Kc that we have been working with. We have the ideal gas constant, we have temperature. So try this calculation for yourself before moving on, but I am going to continue moving on. Our Kp is going to be equal to our Kc, which is 4.65 times 10 to the negative third. Our gas constant R is going to be 0.08206 liter atmosphere per mole Kelvin. Our temperature is 298 Kelvin, and we're going to raise all of this up into the delta N. And so we're looking at the change in moles from reactant to product. But what we are going to be, like how we're actually going to be using these numbers is just like before. We're always going to be looking at a final minus initial type of number. So number of final moles or product moles, and we're going to subtract out the number of initial moles or the number of reactant moles. So this delta N for our provided reaction, since we're looking at a gaseous species here and a gaseous species here, we're looking at the change in the number of gaseous moles, not just moles in general, but it has to be gaseous moles, is going to be 2 minus 1, right? We have 2 moles of product minus 1 mole of reactant, 2 minus 1 here. All right. So the exponent is going to end up just being a 1, so we're basically just multiplying each of these terms in this situation. This exponent, though, will not always be equal to 1. Sometimes it will even be a negative number, and that's totally okay. Sometimes it'll be 0, and that's also okay, but we need to be paying attention to what the numbers of moles here are equal to figure out how this equation is going to work out. So our Kp for this expression, for this N2O4 breaking down into 2 nitrogen dioxides, is going to end up being equal to 0.114. And the difference in these two values then, one being 4 thousandths and the other one being 1/10th, completely has to do with what our perspective is, what our units are in pressure versus concentration. Okay, so here we have an example problem that I definitely, again, suggest you kind of pause, see if you can't figure it out. This is a problem that is based on the previous example that we just worked through, the, interchangeability between Kc and Kp. So the calcium carbonate species in this reaction below we can see is breaking down into calcium oxide and carbon dioxide. This is going to be kind of a combination problem, actually, between all of the concepts we've been talking about today so far, tying them all together. See if we can't draw some information about this chemical equation, about this decomposition, and how much carbon dioxide we'll actually get on the other side. So calcium carbonate is known to decompose at high temperatures. If the partial pressure of carbon dioxide at the end of the reaction is found to be 3.65 atmospheres, and we are, again, working at high temperatures, so something like 1188 Kelvin, what is the Kp and the Kc for this reversible reaction? Okay, so let's look at it, in my opinion, a very fun example. So it's fun because there's a very nice trick to it. You might be thinking, like, I don't have any values for calcium oxide or calcium carbonate. How am I supposed to figure out what my Kc or Kp is equal to if I don't have any type of, like, information aside from the pressure of the carbon dioxide? Well, our Kc and our Kp expressions, let's just write out both of them, observing our reactants and products, and maybe that'll give us a clue as to how we're supposed to progress in this problem. Well, when writing out our Kcs and our Kps, we learned back when it came to heterogeneous equilibria, which is exactly what we're working with, that if all of our species are not in the same phase, we are only going to include aqueous and gaseous species. We do not include liquids and solids. So even though in the wording of this problem we don't have any information for calcium carbonate or calcium oxide, we actually don't need it. These species, since they're solids, we don't include them in our equilibrium expression. Our Kc will end up being equal to the concentration of carbon dioxide. There's no coefficient in front of it, so this is it. Our Kc is equal to concentration of CO2. Similarly, our Kp is equal to the partial pressure of CO2. The other species don't apply. They don't matter. So our equilibrium is going to be solely dictated by the ratio of carbon dioxide to 1. If you have no reactant, if you have no additional product, there's sort of like a 1 as a placeholder there, and any number divided by 1 is itself. So we're just looking at concentration of CO2 or partial pressure of CO2. And so from here, we can now observe the, again, wording of the problem, see if we don't have any information that's going to be useful to us based on either one of these two equations. And yeah, we have a partial pressure of carbon dioxide right here. The Kp is going to be equal to the partial pressure of your carbon dioxide, which is 3.65 atmospheres. And that's it. This 3.65 is going to be equal to your Kp. First problem solved. Now, we also just learned an equation to figure out Kc from your Kp, right? The equation that was Kp is equal to Kc times RT, all to the delta N. So the values that we have so far, we have this 3.63 that we can insert in for our Kp, or 3.65 inserted for our Kp. I just instinctually want everything to rhyme. This is going to be equal to our Kc, multiplied by our value of R, which is our ideal gas constant, 0.08206 units of liter atmosphere per mole Kelvin. And I'm going to bracket this off since it's the gas constant times R. That's all raised up to the delta N, so it's going to be very important to keep this information together. Our temperature is at 1188 Kelvin, and we're going to raise all of this up to the delta N. Now again, the delta N is only going to apply to gaseous species. And so if we observe again our chemical equation, we have a solid, so it doesn't matter. This coefficient of a 1 doesn't get included. We have a solid, this also doesn't matter. This coefficient of 1 doesn't get included. We only have one gaseous species. So if we're looking at moles of product minus moles of reactant, we have 1 mole of gas as a product and 0 moles of gas as a reactant. So our exponent here is going to be that 1 mole of product minus the 0 moles of reactant. And now we have a way to rearrange algebraically and solve for what our Kc is equal to, and our Kc is going to be equal to 0.374. So now we have a value for our Kp. So if we wanted to continue working with this problem from the perspective of partial pressures and gases, we could. If we wanted to continue working with this problem from the perspective of concentrations, we could also do that. We have found all of this equilibrium information just from one partial pressure, as well as knowing what the temperature of the equilibrium or reversible reaction, what it was occurring at. Oh, buddy. Okay, so thank you for bearing with me during this very long introductory lecture to equilibrium. I just wanted to get all of the generic background information kind of out there so we could make sure that we're all starting sort of on the same page, making sure that we're understanding what the nature of equilibrium is, what the equilibrium constant is, how it can be used, and what information it tells us about a reversible reaction. I don't like cutting this lecture off in the middle anywhere, just because then you're left kind of hanging with missing information. You don't see the full context. I will stop ranting now, though. Here we have some section review problems for the equilibrium constant, as well as calculating equilibrium constants. So sort of generic background is the first set of problems, and then more quantitative problems are the second problems. Definitely give both of these sections of problems a try if you would like to try your hand at some more of these problems. Again, I 100% recommend that if this lecture either happened too fast for you, you take the time to go back, maybe listen to certain parts, or again, I would highly recommend reading through some sections in the textbook to kind of give you some additional context for why it is that we are working through these types of problems. But if you do have any questions, anything lingering from after doing your own little bits of research, please, by all means, shoot those questions to me. That way we can talk, figure out how to alleviate any confusion that you might be having. But until next time, class is dismissed.